So now let's see the next part of the chapter, that is equipartition. Okay, so let's talk about equipartition. So what is this? So now we have learned that the kinetic energy, translational kinetic energy of 1 mole of gas is 3 by 2 RT, right? Okay, for n moles it is n times of 3 by 2 RT, 3 by 2 nRT. Okay, for 1 mole it is equal to 3 by 2 RT. Okay, so then this 3 by 2 RT can be written as 3 by 2 times Na multiplied by Kb into T, because we know that the universal gas constant, it is product of Boltzmann constant and Avogadro's number, right? So then now average translational kinetic energy possessed by one molecule of gas would be, it would be equal to what? 3 by 2 Kb into T, because it is just what? It is kinetic energy possessed by 1 mole divided by number of molecules in 1 mole. Okay, so kinetic energy possessed by 1 mole divided by number of molecules possessed in 1 mole, so that Na and Na will get cancelled out. So what remains is 3 by 2 Kb into T. Okay, so this is average kinetic energy of one molecule of a gas. So see, this doesn't mean that every molecule will have only this much amount of energy. Some molecules will have more energy, some molecules will have lesser energy, but the average kinetic energy per molecule would be 3 by 2 kBT, right? This is an average. This doesn't mean that every molecule will have same amount of energy. This is an average. Okay, so this is average translational kinetic energy. Translational means kinetic energy due to linear motion. It is 3 by 2 kBT. Okay, next let's talk about the degrees of freedom. So what are degrees of freedom? So it is number of independent ways of motion due to which a molecule can possess energy. Okay, so number of independent ways in which the molecule can have energy, right? Or we can simply say that if you write the energy of a molecule, then total number of squared terms in that equation is the degrees of freedom. Okay, so we'll talk about it and you will understand it. Okay, for translational motion there would be 3 degrees of freedom. How? Because there are x, y and z components of speed, components of velocity. Okay, so for x direction there can be the molecule can move along x direction, it can move along y direction, or it can move along z direction, right? So there are 3 degrees of freedom, and that's why its energy would be half of kb times t. Okay, so for now there are only 3 degrees of freedom. Okay, so kinetic energy is equal to what? Half of mv square, which can be written as total kinetic energy per molecule. Okay, total average kinetic energy per molecule is 3 by 2 kBt. So that can be written as what? Half of average of half of m into vx square. Okay, see, we are taking average of kinetic energy, that is half of mv square. So okay, so now these angular bracket, this angular bracket means what? It means average. You know this thing? Yes, no? It's there in NCERT, right? So this angular bracket means an average. So average kinetic energy is equal to 3 by 2 kBt, right? So kinetic energy can be written as half mv square, and then that half mv square can be written as what? Because v square is vx square plus vy square plus vz square. Okay, so it can be written as, okay, average of half mv m times vx square plus average of half of m times vy square plus average of half of m times vz square. So you can say this is kinetic energy of motion in x direction, this is kinetic energy of motion in y direction, and this is kinetic energy of motion in z direction, and all 3 directions are equally probable. Okay, so that's why, see, all 3 directions are equally probable. That means molecules moving in x direction is, the probability of that is same as that of molecule moving in y direction, and the probability of that is same as that of molecule moving in z direction. Okay, So the probability of molecule moving in x direction is same as that of it moving in y direction, and it is same as that of it moving in z direction. Okay, and that's why we can just say that this is just equal to 3 times of 3 times of average of half of m into vx square or half of m into vy square, anything. Okay, and therefore you can just cancel it out. Okay, 3 you can cancel out. So what do you get is any one of these 3 terms would be equal to, because they are equally probable, it's equal to half of kb times t, right? It would be equal to half of kb times t. So is this thing clear to everyone? Yes, no? Right, Nikita? Okay, good. All right. So then what is degree of freedom? Degrees of freedom. So it is each independent squared term in the equation of energy of a molecule. So suppose this is equation of energy of a molecule. How many squared terms can be there? So kinetic energy of one molecule can be written as half of m into vx square plus half of m into vy square plus half of m into vz square, right? So there are 3 terms, that means there are 3 degrees of freedom. Okay, there are 3 terms, means there are 3 degrees of freedom. Okay, so this is simple, right? And per degree of freedom, the molecule will have energy equal to half of kb times t. Okay, we have seen this. So this thing is known as the law of equipartition of energy. Okay, this thing is known as what? The law of equipartition of energy. So what is that? A molecule at thermal equilibrium. So this thing is important. At constant temperature, the molecule at thermal equilibrium has equal energy, half of kb times t, associated with each independent degree of freedom. Okay, that means per degree of freedom, the molecule will have equal energy. How much of equal energy? Half of kb times t. Okay, so that is the energy, average energy per molecule, right? So then this is the law of equipartition of energy. Per square term in the equation of energy, the energy would be half of kb times t. Energy of molecule would be half of kb times t. Okay, if there are 3 terms, then it is 3 times half, means 3 by 2 kb times t. Okay, so now we'll apply this to monoatomic molecules, diatomic molecules, etc. Okay, so for a monoatomic gas at temperature T, the average translational kinetic energy would be. So see, what do you mean by monoatomic? What are monoatomic molecules? Helium is there, right? Then all inert gases are there. Okay, helium, neon, krypton, xenon, etc. Okay, so they are all monoatomic, right? So monoatomic gases, so for them, they can only move in space and they can't have any other kind of motion. So therefore their average kinetic energy is just what? Summation of, you can say, half of m vx square plus half of m vy square plus half of m vz square, right? Average of that, and that is equal to half kbt plus half kbt plus half kbt, means it is 3 by 2 kb times t. Okay, so this is very simple, right? And if there are n molecules, okay, then what will you have? So that n can be written as n times of Na. Okay, n can be written as capital N is number of molecules. It can be written as number of molecules in 1 mole, Na, times number of moles, right? So then the average kinetic energy of n molecules, that means small n number of moles, can be written as what? 3 by 2 n times of Na multiplied by kBt. So you have just multiplied this thing with small n times of Na, okay, and then Na times Kb, we know it is equal to R. So this is equal to 3 by 2 nRT. Okay, so actually we had seen this equation earlier also. Okay, from kinetic theory of gases we derived that average kinetic energy is equal to what? 3 by 2 nRT, right? Okay, so this is true for monoatomic gas. The average kinetic energy is equal to 3 by 2 nRT, or average energy you can say. After that, let's say let's see energy of diatomic molecule. Okay, energy of a diatomic molecule. So there are two atoms. For example, you have hydrogen, oxygen, okay, nitrogen. All the major constituents of air have diatomic molecules. Okay, so a diatomic molecule at low temperature has 3 translational and 2 rotational degrees of freedom. How? So suppose you have this molecule. Okay, this is a diatomic molecule. For an example, it is H2. So this thing will be HH, right? So then now this molecule as whole, okay, so this molecule as a system, it can move in space, right, in x direction, y direction, z direction, or suppose it is moving in some direction, so its velocity can be resolved along 3 directions, right? So that molecule can move in space. Then what else can it do? So this molecule, it can move in space as well as it can rotate like this. Okay, so it will move in space, the molecule will move in space, also it will rotate, the molecule will rotate about this y-axis, or let's say this is x-axis. Okay, so see, there can be only two axes for its rotation, two independent axes, because along third direction there will be the bond, right? The length of the molecule, or you can say the bond is along one direction, you can say this is x suppose, then this molecule can rotate about y-axis, or it can rotate about z-axis. So for two rotations there would be 2 degrees of freedom, okay, or 2 square terms of kinetic energy. So we know that if something rotates, any system rotates, then what is its rotational kinetic energy? Half of I into omega square, right? What is the rotational kinetic energy? It is half of moment of inertia multiplied by omega square, angular velocity square. So if this one rotates about the y-axis, then its rotational kinetic energy would be half of Iy, means moment of inertia about y-axis, times omega y square. Okay, if it rotates about the z-axis, then it would be half of Iz times omega z square. Okay, so three terms for translational kinetic energy and 2 terms for rotational kinetic energy. So total 5 terms, okay, 5 square terms, and that's why there are 5 degrees of freedom, and that's why its energy per molecule would be equal to what? 5 times of half of kBt, that is 5 by 2 kBt. Okay, is this thing clear? Energy of a diatomic molecule would be 5 by 2 kBt. Yes, everyone? Right, good. So then this is true for a rigid molecule. Okay, this is true for which kind of molecule? Rigid molecule. Okay, so now see what will happen at very high temperatures. So at very high temperatures there would be another degree of freedom. That means now what are these molecules doing? At low temperatures they are moving in space and also they are rotating. Okay, so they are moving in space and also molecules are rotating. So you can say that molecules are rotating and moving in space. Okay, then now if temperature increases, what happens is the molecules also begin to vibrate at very high temperatures. Okay, at very high temperatures molecules also begin to vibrate. Okay, so now this temperature at which the molecular vibrations will activate is different for different molecules. Okay, and most probably it will be given in the questions, or they will just say at very high temperature. Okay, so then the molecules will also vibrate, so there is a vibrational degree of freedom. okay, right? So that molecule, we'll call it as a non-rigid molecule, okay. It can be called a soft molecule or flexible molecule, but the standard term is non-rigid molecule. So how many degrees of freedom are there? 3 translational degrees of freedom, 2 rotational degrees of freedom. It will do this kind of motion, okay. It will rotate and move in space, rotate and move in space, okay. This kind of motion it is doing at low temperatures also, as well as 2 vibrational degrees of freedom. Now you might ask, it will vibrate if there is only one bond, so it might vibrate along that bond only. So why 2 degrees of freedom? Because there are the vibrational energy is equal to what? Sum of vibrational potential energy and kinetic energy, okay. So total it is half of m v square, but this v is vibrational speed of this molecule, so half of v square plus half of k times x square, okay. If it is vibrating, right, so you can think of a bond like spring, then its potential energy would be equal to half of k into x square. So there are 2 square terms, that means there are 2 degrees of freedom, okay. So total degrees of freedom is 3 plus 2 plus 2, that means 7, and that's why the energy of this molecule would be equal to what? It would be equal to 7 by 2 kb times T. Is this thing clear? Okay, 7 degrees of freedom, so 7 times half of kBT. Okay, this is clear, everyone? All right, very good. So this is energy of a diatomic molecule at very high temperatures, okay. But for monoatomic molecule, whether the temperature is low or temperature is high does not matter, its energy will remain same, okay. That's 3 by 2 kBT. All right, then we'll discuss the molar heat capacity, okay. All right, so then we'll talk about the molar heat capacities of gases. So now for an example, suppose you have this container and its volume is fixed and you heat this container. So this container contains some gas, okay, and you heat it, right, you heat it. So now what will happen? So the volume is fixed, okay. So now we know what is the specific heat capacity, sorry, molar heat capacity. It is the amount of energy required to raise the temperature of 1 mole of gas by 1 degree Celsius, or you can say 1 Kelvin, right. So C is equal to delta Q divided by delta T for 1 mole, okay. N is equal to 1. So now if volume is fixed, that means there is no work being done, okay. So all of the energy that you are giving, it is only utilized in increasing the internal energy of the substance, okay, that means the gas, okay. So for fixed volume of gas, the heat given is completely utilized in increasing the energy of the gas only. So delta Q is the amount of heat given and it is only equal to what? Delta U. Delta U is what? It is the change in internal energy, okay. So now we know for a monoatomic gas, U is equal to what? 3 by 2 RT, okay, for 1 mole. For 1 molecule it would be 3 by 2 kBT, for 1 mole it would be equal to 3 by 2 RT, right. This is for 1 mole. And then therefore what would be its specific heat? Again I said specific heat, sorry, molar heat capacity. Its molar heat capacity would be equal to amount of energy taken, right, amount of heat energy taken. So heat energy is just equal to what? Change in the internal energy, right. So change in internal energy per degree rise in temperature, okay. So CV, why CV? Because its volume is constant, so CV is equal to dq by dt, okay. dq by dt means change in the amount of heat taken per unit change in temperature, okay, for 1 mole of gas. So we have seen that change in Q is equal to change in U, that means change in internal energy. So that's why it is equal to, it is just equal to du by dt, and U is equal to 3 by 2 RT. So take its derivative with respect to T. So 3 by 2 RT, take its derivative, so 3 by 2 R, you can move outside, then what remains is dt by dt, dt by dt is 1. So therefore, what is the CV? CV is 3 by 2 R. Okay. Molar heat capacity at constant volume is 3 by 2 R. Is this thing clear, everyone? Right. So this is molar heat capacity at constant volume. After that, let's talk about the molar heat capacity at constant pressure. Okay, so molar heat capacity of monoatomic gas. Okay, so that is for monoatomic gas at constant volume is CV is equal to 3 by 2 R. Now, suppose you have this gas again in this container and there is a piston. Okay, there is a piston. Now, the piston is just kept. It is airtight, but it is just kept over this gas. Okay, so what would be the pressure over there? Pressure is just equal to the atmospheric pressure. That means pressure is constant. Okay, the pressure is constant. Outside pressure is constant. Okay, so now suppose you provide some energy to this gas. The earlier one was a closed container. Here you have this piston which can be lifted. That means the volume of this gas can increase. So volume is not constant. Okay, what is constant? Pressure is constant because the piston is just kept. Okay, that means the pressure would be equal to atmospheric pressure. Okay, so now consider monoatomic gas at constant pressure. Now the energy given is utilized. The energy that you give, that means heat energy that you give, it is utilized in two ways. So one is to increase the internal energy, of course, and the second thing is to do some work against the surrounding. Okay, so to lift this piston, you can say, right? Okay, so gas will expand. Okay, gas is expanding. So how much of work is done? So see, okay, first of all, the energy given delta Q is equal to what? It is utilized in two ways. One is to rise the internal energy. Okay, so change in internal energy, plus second thing is to do some work. Okay, to expand, right? So delta W is the amount of work done. Okay, so then the work done can be written as what? So you can write the work done is equal to force into displacement. And how much of force would be there? How much of force would be there? So since pressure is constant, the internal pressure would be just equal to the external pressure, that is atmospheric pressure. Okay, so pressure is P. How much of force is there? So see, this works in this way. Internal pressure, even if it is slightly greater, okay, infinitesimally greater, okay, with that means greater by very small amount than the external pressure, still it will expand. Okay, it will expand till the time the internal and external pressure become what? Equal. Okay, so system is in equilibrium, right? There is slight separation, okay, from the equilibrium, the system will expand. Okay, so that's why we are taking pressure to be constant only. So how much of force will be there? Pressure times area, because pressure is force divided by area. Okay, so the force is pressure times area, and suppose the expansion is, that means displacement is delta x. Okay, so displacement is delta x. Then what is A times delta x? So you can see here A times delta x is increase in volume, change in volume. Okay, A times delta x is change in volume. So that is delta V. Okay, so delta Q is equal to delta U plus P times delta V. Okay, delta Q is equal to delta U plus P times delta V. Okay, this thing is clear? Yes, no? Everyone? Right. So what we used here is the law of conservation of energy, okay, or you can also say that it is the first law of thermodynamics, right? Yes, no? This thing is clear? All right. Okay, then what did we say? That amount of energy absorbed, okay, amount of heat energy taken is equal to delta U plus P delta V, okay, and we know PV is equal to nRT, okay, PV is equal to nRT, and N and R are constants, number of moles, and R is a constant, R is universal gas constant, okay. So therefore P times delta V would be equal to what? Nr times delta T only, okay, Nr times delta T only, right? So then for 1 mole it would be just equal to what? R times delta T, okay, for 1 mole it would be just equal to R times delta T, right? So therefore now we can find out the molar heat capacity at constant pressure, okay. Now what is that? So it is the amount of heat taken by the gas per degree rise in temperature at constant pressure, okay, at constant pressure. So we have seen that this heat taken can be written in two ways, okay. Delta U can be written as delta U plus or delta W, and we found that delta W is P delta V, and that is equal to what? R times delta T, okay. So if we just substitute that, okay, so delta Q is equal to what? Delta U plus P delta V, right? We are writing D for delta, so this is written in differential form. It means that the change in U or change in any quantity is very small, okay. So because we are taking derivatives, so dq can be written as what? Du, right? Delta is replaced by D plus P delta V, that means P dV, okay. And then P dV can be written as what? R times delta is replaced by D, okay, everywhere. So R times dt, okay. So P dV can be written as R times dt. So what do you get then? So you have already found what is du by dt for monoatomic gas. U is equal to what? 3 by 2 RT, okay, it is equal to what? 3 by 2 RT, right? And then you have P dV, it is R times dt, okay. So then if you take its derivative, so derivative of this 3 by 2 RT is 3 by 2 R, and derivative of this thing, so R you can take outside anyways, it is just dt by dt, dt by dt is 1. What do you get? Cp is equal to, so this thing is Cv everywhere, okay. So here for monoatomic gas it would be equal to 3 by 2 R, right? It's equal to 3 by 2 R plus R, 3 by 2 R plus R means 5 by 2 R, okay. 3 by 2 R plus R means 5 by 2 R. This is molar heat capacity of a monoatomic gas at constant pressure, okay. Long term molar heat capacity of monoatomic gas at constant pressure is 5 by 2 R. Is this thing clear, everyone? There is a relation which relates Cp to Cv, and that is Cp minus Cv is R. The difference between the molar heat capacity at constant pressure and molar heat capacity at constant volume is equal to what? R, the universal gas constant, okay. So it can be understood here itself. So this is Cp, and Cp is equal to what? Du by dt, and we have seen earlier that what is du by dt. So du by dt is Cv, right? Du by dt is Cv. So here itself you get Cp is equal to what? Du by dt means Cv times P dV by dt, that is P dV can be written as what? This thing, R times dt by dt, means this thing is R. So Cp is equal to du by dt means Cv plus R everywhere, okay. It is this relation. So here we didn't consider whether it's monoatomic, diatomic, okay. We substituted 3 by 2 RT for U in this term, okay, in this step, right? So till here this was completely general. That means this relation is applicable to any kind of gas, that Cp minus Cv is equal to R, right? Is this thing clear? Yes, no, right? Okay, then you can take the ratio of molar heat capacities. So what would be the ratio of molar heat capacities? It is Cp divided by Cv. Okay, molar heat capacity at constant pressure divided by molar heat capacity at constant volume, and it is just 5 by 3 for monoatomic gas. Okay, it is 5 by 3 for monoatomic gas, right? Because Cp is 5 by 2R and Cv is 3 by 2R. Okay, so RR gets cancelled, that 2 gets cancelled, so what remains is 5 by 3. So very simple, right? After that, yeah, so we are discussing molar heat capacities, and we have seen for monoatomic gas that energy per mole is equal to what? 3 by 2 RT, and therefore Cv would be equal to du by dt, which is 3 by 2 R, right? If you substitute u is equal to 3 by 2 RT, and then Cp is just equal to what? Cv plus R, and that is 5 by 2 R. This is what we have seen. And then if you take ratio of Cp to Cv, that's gamma is Cp divided by Cv, and it's 5 by 3. Okay, then next is diatomic gas, but first we'll consider rigid diatomic gas, means diatomic gas at lower temperature. Okay, so energy per mole is given by this formula, u is equal to 5 by 2 RT. We have seen this. Okay, so then Cv is just equal to du by dt, and that is 5 by 2 R. Okay, this is rigid diatomic gas, rigid diatomic gas. Okay, so Cv is equal to 5 by 2 R, Cp is just 5 by 2 R plus R, and that is 7 by 2 R, and then gamma is ratio of Cp to Cv, and Cp to Cv is 7 by 5. Okay, 7 by 2 R divided by 5 by 2 R, so it gives you 7 by 5. So this is a rigid diatomic gas. Now, if it is non-rigid diatomic gas, so then what happens is energy per mole, we have seen this, it would be equal to 7 by 2 RT. So U is equal to 7 by 2 RT. Find Cv. So Cv would be equal to du by dt, that is 7 by 2 R, right? Because U is equal to 7 by 2 RT. Then what would be Cp? Add one extra R. Okay, so Cp is Cv plus R. So that is 7 by 2 R plus R, means 9 by 2 R. Okay, and then find Cp by Cv. So Cp by Cv for a non-rigid diatomic gas, gamma is equal to what? 9 by 2 R divided by 7 by 2 R. So that means 9 by 7. Okay, 9 divided by 7. So this is for non-rigid diatomic gas. Okay, is it clear till this point? All right, so next is polyatomic gases. So degrees of freedom of polyatomic gases would be 3 translational, 3 rotational. Okay, 3 translational, 3 rotational. Why? Because 3 translational is fine. Okay, everybody understands this. So degrees of freedom of a polyatomic gas would be 3 translational, right? Because it can move along x, y and z axis. Then if there are n number of atoms in a molecule, then what will happen? It can rotate about an axis, x axis, it can rotate about y axis, it can rotate about z axis. Okay, it can rotate like this. Okay, it can rotate like this, and then let's say this is x axis, it can rotate like this also. Okay, like this, it can rotate like this. Okay, and then it can rotate like this, x, y, z. Okay, right? Simply because there would be more number of bonds. Is this thing clear? So there would be 3 rotational degrees of freedom. Okay, and here let's change this n to f, or some other letter, because we should not get confused with number of moles, right? So let's say p vibrational modes. Okay, p vibrational modes. All right. Okay, so then it has 3 translational, 3 rotational, and I have changed this n to p because not to get confused with the number of moles. So suppose there are p vibrational modes. So this polyatomic, the molecule, polyatomic molecule can vibrate along what? All of its bonds, right? This thing is clear. So polyatomic molecule will have 3 translational degrees of freedom, for one along x-axis, one along y-axis, one along z-axis. Then 3 rotational degrees of freedom, because it can rotate about 3 axes. There are simply more number of atoms. Okay, that means there are more number of bonds. So it can rotate about x-axis, y-axis and z-axis. And also there would be p vibrational modes. So the polyatomic molecule can vibrate along each of its bond. Right, it can vibrate along each of its bond. Okay, this thing is clear. So suppose there are p vibrational modes, that means it can vibrate along p bonds. Okay, p number of bonds, right? So then what do we get here? So for each vibrational mode there are 2 degrees of freedom. One is what? The kinetic energy, and one is potential energy. So that's why for each vibrational mode there are 2 degrees of freedom. So here there will be 2p. Okay, vibrational degrees of freedom, right? So then what do we get? So the energy per degree of freedom, here it would be for translational degrees of freedom, it would be 3 by 2 RT. Here it would be 3 by 2 RT for rotational degrees of freedom, and here it will be PRT. Okay, here it would be PRT. This thing is clear? Yes, no? Yeah. Okay, because see, we have seen law of equipartition of energy, that per degree of freedom the molecule will have energy equal to 3 by 2 kBT, molecule of a gas. Sorry, what did I say? 3 by 2 kBT. So for each degree of freedom the molecule will have half of kBT amount of energy. If you consider 1 mole, then it will have half of RT amount of energy per degree of freedom, right? So this molecule has 3 translational degrees of freedom, means 3 times of half of RT. Okay, so 3 by 2 RT for translational motion, 3 by 2 RT for rotational motion, and then half of RT multiplied by 2p. Okay, for vibrational modes. Okay, so for vibrational degrees of freedom, so it is half of RT times 2p, so that 2 and 2 gets cancelled, that's why PRT. Okay, that's why what do you get? P times RT. Okay, is this thing clear, everyone? Yes, no? Right. And then what we get is 3 by 2 RT plus 3 by 2 RT would be 3 RT, 3 RT plus PRT. So what we can do is take RT common, so it will be 3 plus P, right? 3 plus P. Okay, for P vibrational modes. So that much is amount of energy possessed by a polyatomic gas. Okay, amount of energy possessed by a polyatomic gas, and then its CV would be equal to what? Take du by dt. So du by dt would be equal to 3 plus PR, because if you take derivative of this thing, it will be 3 plus PR dt by dt, that means 3 plus PR. And then what would be CP? Okay, so that was CV. So what would be CP? Cp would be 1 extra r, so that is 4 plus Pr. And then if you want gamma, okay, so gamma is just Cp divided by Cv, so it is 4 plus P divided by 3 plus P, right? 4 plus P divided by 3 plus P. So what is P here? So P is number of vibrational modes. What is P? P is the number of vibrational modes. So is this thing clear, everyone? Is this formula clear? Right? Okay. So now we'll solve some problems based upon this thing. Okay. So let's see this one. Assertion is vibrational degree of freedom of a diatomic gas molecule appears at every high temperature. Okay. Reason is diatomic gas has 2 vibrational degree of freedom in one direction. Okay, tell me. So vibrational degree of freedom of diatomic gas molecule appears at every high temperature. Actually it should be very high temperature, not every high temperature. Okay, I think this it's a typing mistake. Okay, and diatomic gas has 2 vibrational degree of freedom in one direction. So this is correct. For one direction there will be 2 vibrational degrees of freedom, because for every vibrational mode there are 2 degrees of freedom, one due to potential energy, one due to the kinetic energy, and this is also correct. But does this explain this thing? It doesn't explain, right? Yes, no? Okay, so answer is both are correct, but B doesn't explain, the B doesn't explain A, means reason does not explain the assertion. So both assertion and reason are correct, but reason is not correct explanation of assertion. This should be the answer. Okay. Alright, so this is very simple. Let's see next one. Assertion, the molecules of monoatomic gas has 3 degrees of freedom. So is that correct? Yes, no? It is correct, right? Monoatomic molecule has only translational degrees of freedom, that means linear degrees of freedom, so that is 3. And then the molecules of diatomic gas has 5 degrees of freedom. Okay, so this can be reason for this one. Okay, so this one is also correct. Diatomic gas has 5 degrees of freedom in general. In general meaning if temperature is not stated, if temperature is low. Okay, so it will have 5 degrees of freedom. It is correct. So both are correct, but this doesn't explain this one. Okay, so both assertion and reason are correct, but reason is not correct explanation of assertion. So it is also option B, right? Okay, good. Let's see next one. So this is from NEET 2020. The average thermal energy for a monoatomic gas is, tell me how much is the average thermal energy for a monoatomic gas. They ask direct question. Yes, it's option B, everyone. Right, it is option B. Very good. Okay, very simple, straightforward question. Let's see next one. The number of translational degrees of freedom for a diatomic gas is, okay, tell me. Okay, everyone. It should be 3. Okay, whether it's diatomic, triatomic, it's a molecule as a whole can move along x-axis, y-axis or z-axis, that's it, right? So number of translational degrees of freedom is just 3. Okay, so for diatomic molecule or any polyatomic molecule, what is extra? The rotational and vibrational degrees of freedom are extra. Okay, so that is translational is only 3. All right, let's see next one. A polyatomic gas with n degrees of freedom. Okay, so now they have written n here. n degrees of freedom has mean energy per molecule given by? Okay, tell me. So it is just C. Option C, yeah, that's correct. Okay, per degree of freedom, apply law of equipartition of energy. The energy per degree of freedom would be just equal to what? Half of kb times T, half of Boltzmann constant times T. So for n degrees of freedom, it would be just n times kb T by 2. Okay, n times of half of kb T, that is n times kb T by 2. That's option C. Very simple, right? These are all fact based questions. Okay, so very simple. Yes, this is clear. Nikita, Indusha, Selva Kumar.
Yes, sir.
Okay, good. Let's see next one. The ratio of specific heats. Okay, actually it is molar heats, but they are saying specific heats. That is fine. And ratio of specific heats will also be same, right? Because there is only one okay, m factor extra, right? We have seen the relation between specific heat and molar heat. Okay, all right. So ratio of specific heats Cp by Cv equal to gamma in terms of degrees of freedom n is given by. Okay, tell me. All right. So how can we write Cv? First of all, U can be written as the energy of a gas can be written as what? It can be written as n times, n is a number of degrees of freedom, times half of kBt. Okay, half of kBt, right? For 1 mole, it will be half of RT. Okay, so this is n by 2 RT, right? This is U. What will be Cv? So Cv is just equal to, take its derivative, du by dt. Okay, so it is n by 2 R, right? And what is Cp then? Cp is Cv plus R, Mayer's relation. Okay, so n by 2 R plus R, so n by 2 plus 1 R, this is Cp, and you want Cp by Cv, so gamma is equal to Cp by Cv, that is equal to here n by 2 plus 1 divided by n by 2, and you have R and R in numerator and denominator, that gets cancelled out. So then you just multiply this with 2, so you get n plus 2 divided by 2 divided by n by 2, that 2 will get cancelled. So n plus 2 by n plus 2 divided by n. Okay, and then you can divide this thing, so you get 1 plus 2 by n. Okay, as in options it's given in that way. So it is 1 plus 2 by n. That is the answer, option C. Okay, this thing is clear, everyone? Okay, so I started from very basics here, but you can start here itself. Okay, Cv is equal to what? Number of degrees of freedom multiplied by R. Okay, Cv is equal to number of degrees of freedom multiplied by, sorry, I said R by 2. Okay, number of degrees of freedom multiplied by R by 2. Okay, very simple. All right, there is some calculation, right? Some calculation, otherwise there is nothing. Okay, let's see next question. This is from NEET 2019. The value of gamma Cp by Cv for hydrogen, helium and another ideal diatomic gas X whose molecules are not rigid but have additional vibrational mode. Okay, so instead of explaining all this, they could just say that it is at high temperature. Still the answer would be same. Okay, are respectively equal to, tell me. So hydrogen means diatomic, okay, for diatomic or mono, but diatomic rigid, okay. First one is diatomic rigid, second one is monoatomic, helium is monoatomic, and third one is X is diatomic non-rigid, okay, di non-rigid. Okay, tell me what's the ratio? Option A, for diatomic rigid it's 7 by 5, for monoatomic it's 5 by 3, and for this one non-rigid it is 9 by 7. That's correct, it is option A. Okay, again a fact-based question, simple question, right? Okay, so we have seen gammas for all of them, right? Gamma means the ratio of specific heat or molar heat capacities. Okay, let's see next one. A gas mixture consists of 2 moles of O2 and 4 moles of air. Air is argon, right? At temperature T. Neglecting all vibrational modes, the total internal energy of the system is. So what would be the total internal energy of the system? So U is equal to, let's say, energy of oxygen plus energy of argon, right? And then how many number of moles are there? 2 moles and 4 moles. So 2 times energy per mole of oxygen. Oxygen is diatomic, right? This is diatomic. So energy per mole would be what? 5 by 2 RT plus energy of argon. Argon's 4 moles are there. So 4 times energy per mole, and argon is monoatomic, and that's why it is 3 by 2 RT. Okay. Then just cancel out this 2, so this is 5 RT plus then 4 divided by 2 is 2, 2 times 3 is 6 RT. So 5 plus 6 is 11. So the answer is 11 RT. Okay, so it is option C. Right, this thing is clear. Okay, everyone. All right, good. Good. Let's see next one. The amount of heat energy required to raise the temperature of 1 gram of helium at NTP from T1 equals to T1 Kelvin to T2 Kelvin is. So how much of amount of energy would be required to raise the temperature, okay, of helium at NTP from T1 Kelvin to T2 Kelvin? Okay, tell me. Okay, so see, you have U equals to, okay, internal energy is equal to what? How can you write internal energy? So it is 3 by 2 RT for 1 mole, right? Internal energy is 3 by 2 RT, okay? So its internal energy is equal to 3 by 2 RT, okay? So how much of energy is required to raise its temperature, okay, to raise its temperature from T1 Kelvin to T2 Kelvin, right? So this is internal energy per mole. Now how many moles are there? So let's write internal energy is equal to what? N times of 3 by 2 RT. How many moles are there? So for helium, the molar mass is equal to what? 4 grams, right? And there is only 1 gram here. Okay, so mass is equal to 1 gram. So what does it mean? The number of moles is equal to mass divided by molar mass. Okay, so that is 1 by 4, right? So it is 1 by 4. So energy would be equal to what? 1 by 4 times 3 by 2 RT. And you are raising its temperature from T1 to T2. Okay, so the energy required would be equal to delta U. Delta U is just equal to what? You can just write it as U2 minus U1, and that is equal to 1 by 4 times 3 by 2 R. You can take common. Okay, so how much is that? Actually 3 by 8 R. You can take common, and it is T2 minus T1, right? But then they have given it in N times Kb, and we know that R is equal to what? R is equal to the product of Boltzmann constant and Avogadro's number. So Na times Kb. So you can write this R as Na times Kb. Okay. So Na times Kb, T2 minus T1. Right, this thing is clear, everyone. So this is the answer. Yes, no? Okay, so this much energy is required to raise its temperature. Okay, so it's option C. All right, so then let's see next one. The molar specific heat at constant pressure of an ideal gas is 7 by 2 R. The ratio of specific heat at constant pressure to that of constant volume is. Okay, so very simple. What is given? Cp is given, right? Constant pressure is given, no? At constant pressure, Cp is equal to 7 by 2 R. That means what would be Cv? Cv is Cp minus 1 R, that is Cp minus R. 7 by 2 R minus R is 5 by 2 R, and therefore what would be the ratio of specific heat capacities? So gamma is Cp by Cv, and that is equal to 7 by 2 divided by 5 by 2, so 7 by 5. Okay, so it is option B. Right, this is option B. Okay, this one is clear. This is very simple, right? Yes, no? All right, good. Let's see next one. To find out degrees of freedom, the expression is, to find out degrees of freedom, which one is the expression out of this? So F is degrees of freedom. Okay, F is what? Degrees of freedom, right? So then see, we can write where does the gamma come from? We know Cv is equal to number of degrees of freedom, that is F, multiplied by what? 1 by 2 R. Okay, so we can say F by 2 R. What is Cp? So Cp is equal to what? F by 2 plus 1 R. Okay, that's difference between Cp and Cv is R. So F by 2 plus 1 R. And then what would be gamma? So just take ratio of them. So it will be F by 2 plus 1 divided by F by 2, right? F by 2 plus 1 divided by F by 2, and we can move that F by 2 on other side. So what do we get? Okay, what do we get is F by 2 times gamma is equal to F by 2 plus 1, and we wanted F only, right? So let's multiply this equation by 2. So we get F times gamma is equal to F plus 2. We can move this F on other side, and we can take it common too. So F times gamma minus 1 would be equal to 2, right? And then gamma minus 1 on other side. So F is equal to 2 divided by gamma minus 1. So that's the answer. So it is option A, right? Yeah, option A. Okay, this one is clear. Yes, no? Okay, good. Let's see next one. If quantity of heat 1163.4 joule supplied to 1 mole of a nitrogen gas at room temperature and constant pressure, then rise in temperature is. Okay, so they are saying it is constant pressure. Okay, heat is supplied at room temperature and constant pressure, then rise in temperature is. Okay, tell me. So they are saying constant pressure, so we need to take Cp, right? If they say constant volume, we'll take Cv. So this is constant pressure, so that is equal to 1163.4, okay, or Cp is equal to delta Q divided by delta T, right? And we want delta T, the change in temperature or rise in temperature. So delta T is just equal to delta Q divided by Cp. What would be Cp? Tell me. This is which gas? Nitrogen gas. What would be Cp? 5 by 2R, 7 by 2R, 9 by 2R. What? Yes, anyone? Anyone? Cp would be equal to 7 by 2R, right? This is diatomic, no? So Cv is 5 by 2R, okay, because they have not given high temperature, etc. So Cv is just what? 5 by 2R, and Cp is Cv plus R, so that is 7 by 2R, right? So Cp is 7 by 2R, and we want change in temperature, so amount of heat is given, and they assume that we know that Cp is equal to 7 by 2R for a diatomic gas. So let's put the values. So it is delta Q is 1163.4 divided by 7 by 2R. Take that 2 in the numerator, so you get delta T is equal to 2 times of 1163.4 divided by 7 times of 8.314, right? R is 8.314, so this is 56, okay, 56, and this thing would be equal to, okay, this thing divided by 56, how much? 20. We multiply this thing by 2, what will you get? You will get 112. Okay, so close, right? 112, close. So this will be 20 times 2, 40. Yeah, roughly 40 K. Okay, why K? I mean, change in temperature can be written in degree Celsius or kelvins, right? Then if for a gas R divided by Cv is equal to 0.67, this gas is made up of molecules which are, tell me. R divided by Cv, so this is very good question, right? Very simple, this is very old, okay. So R by Cv is given, so just find out Cv, right? So Cv is equal to what? R divided by 0.67, okay, right? And what is 0.67? 0.67 can be written as 2 by 3, right? 2 by 3 will give you 0.6666 recurrent, okay. So this thing is 2 by 3, so move that 3 in numerator, so you can write this thing is equal to 3 by 2, okay, and that's why the answer is monoatomic, right? Cv is equal to 3 by 2R, so it is monoatomic. Okay, very simple, good. Let's see next one. For hydrogen gas, Cp minus Cv is equal to A, and for oxygen gas, Cp minus Cv is equal to B. So the relation between A and B is given by, yes, tell me. Relation between A and B is given by, what is Cp minus Cv? Tell me. what happened? Cp minus Cv is R, right? Whether it's oxygen, whether it's hydrogen, doesn't matter. Cp minus Cv is equal to R. Okay, universal gas constant, we know that. This is Mayer's relation. Okay, so then A is equal to R and B is also equal to R. So that means A is equal to B. Okay, this is the simplest question, isn't it? So next, let us talk about the mean free path. Now, what is this? So let me explain it well. Okay, so suppose we have some gas. Okay, so let's suppose this is some gas molecule and it's moving in this direction. Okay, and there are other gas molecules in the surrounding, right? These are other gas molecules in the surrounding region, and now this molecule can collide, this one can collide with n number of molecules, and the average distance that it covers between two successive collisions, that is called as mean free path. Okay, the average distance up to which it can move freely without colliding, right? It is known as the mean free path. Okay, so let's see mean free path. So suppose this molecule moves in this direction and its diameter is equal to d. Okay, what is d? Can you see this? This molecule is moving, okay, in this direction. Its diameter is equal to d. Then see, it can hit with other molecules which come in this much area. So suppose it is moving, okay, in this direction. So how much of cross sectional area will it cover? It will cover cross sectional area equal to pi times d square. You cannot say pi r square because you cannot say pi r square because of what? It will not just collide head on. Head on means straight, okay, head to head. Okay, it can collide, it can just collide with a molecule, okay, which will come even here. That means at the end also. Okay, so that's why it is not just area of cross section in which it will collide, right? This is area of cross section in which it will collide. It is not just pi r square, it is pi d square. It will cover this much area because it cannot just collide with these molecules which collide with it head on. It can also collide with the molecules, okay, which are slightly off the center, you can say, right? Not slightly, even up to the end, you can say, right? Yes, no. So if some molecule is over here, it can collide with this molecule also. Okay, this thing is clear why the area in which it can collide is pi d square and not pi r square. Okay, good. So d is diameter, r is radius. Okay, so then now total number of collisions in some time delta t. Okay, in time delta t, how many collisions would be there? So suppose it sweeps out the volume equal to V, capital V, in time delta t, right? Sweeps out means it can move through the volume equal to V. So what is that volume? Okay, what is that volume? Volume swept by this molecule can be written as this area, effective area of cross section in which it can collide, multiplied by the distance through which it moves. So it is pi d square multiplied by the distance. Distance is what? Its average velocity times delta t, right? Its average velocity times delta t. Okay, so then I'm sorry, then volume swept, okay, so how many, again, Okay. So this is the volume swept out. Then how many collisions can be there? So the number of collisions would be equal to the volume through which it moves, volume swept out, multiplied by number of molecules per unit volume. Okay, so that is number density of molecules, right? So suppose there are n number of molecules, total number of molecules is n, divided by volume is v. So n would be the number of molecules per unit volume, right? Small n is what? Number of molecules per unit volume. So the number of molecules per unit volume times the volume through which it moves, volume swept out, is the number of collisions, because it will collide with every molecule that comes within that volume, right? Okay, so therefore total number of collisions would be equal to volume swept multiplied by number of molecules per unit volume. Okay, so volume swept is this much, pi d square times of v delta t. Okay, right? Volume swept would be equal to what? Area of cross section multiplied by distance through which it moves. So area of cross section is pi d square, and distance through which it moves is average velocity times the time. Okay, so this is the volume swept multiplied by, you have n divided by v, and this is number of molecules per unit volume, so that is small n. Okay, so you have pi d square times v bar into n delta t. So this is what? Number of collisions, right? This is number of collisions. What would be frequency of collisions? So frequency of collisions is number of collisions per unit time. Okay, so number of collisions per unit time is frequency of collisions. So then there is pi d square times v bar n delta t upon delta t. So that delta t gets cancelled out. Okay, delta t gets cancelled out, and then you get f is equal to pi d square v bar times n. Okay, n is number of molecules per unit volume, v bar is the average velocity, and then you have pi d square. Okay, and then average time between collisions would be equal to what? The average time between two collisions would be just reciprocal of frequency. Okay, average time between collisions. So we know time and frequency, they are reciprocals of each other, time period and frequency. So what would be average time? That means we can say it is average time period of the collisions. So that's reciprocal of frequency. So that means it is 1 upon pi d square v bar times n. Okay, and then therefore the mean free path, so the average distance that it travels without colliding is equal to what? Its velocity, average velocity, times the average time between two collisions. Okay, so v bar times tau. Tau is the average time between collisions. So if you multiply that with this, then v bar and v bar gets cancelled out. So what remains is 1 upon pi d square times n. Okay, so mean free path would come equal to this thing if only this molecule is moving and other molecules are steady. Okay, if only this molecule is moving and other molecules are steady, then mean free path would come out to be equal to 1 upon pi d square times n. But now we know that other molecules are also moving. Okay, other molecules are also moving. So for that, what we do is we take into account that fact, and then the formula gets modified by root 2. Okay, the formula gets modified by root 2. So frequency of collisions, etc., and time between two collisions, we don't need to remember this formulae. We just need to remember the mean free path. Okay, so mean free path would be equal to 1 upon root 2 pi d square times n. Is this thing clear, everyone? Yes, no? Okay, this formula is clear. So mean free path is equal to 1 upon root 2 pi d square times n. Okay, and then now if we ever want this formula, then we know that lambda mean, this is important, this we need to remember, that it is 1 upon root 2 pi d square times n. Okay, and if we want, let's say, the time between two collisions, then we can just say that lambda mean is equal to mean free path is equal to average velocity times the average relaxation time or average time between two collisions. Okay, that is tau. So tau is just equal to what? Lambda mean divided by this v bar. Okay, so write down the formula of lambda mean. Take v bar on other side. Okay, so it comes out to be equal to lambda mean, which is 1 upon root 2 pi d square times n divided by v bar, so that v bar will come in denominator, right? This thing is clear, everyone? So no need to remember this formula or this formula. Okay, that will be an extra. Just remember this one. Okay, because the stated topic in the syllabus is mean free path, right? So mean free path we must remember, and these are just, I mean, related quantities, related terms. So even if there is a question based upon that, we can just find it out. Okay, if we know the concept, of course, that lambda mean is equal to what? Average velocity times average time between two collisions. Okay, so what would be average time between collisions? Lambda mean divided by average velocity v bar. Okay, this is clear, everyone? All right, good. So then let us see question based on this. Okay, so let's see this question from NEET 2020. The mean free path for a gas with molecular diameter d and number density n can be expressed as. Tell me what's the formula? It's option B. Okay, it's option B, right? Let's see another question. The mean free path of molecules of a gas is inversely proportional to, r is the radius, okay, then it's inversely proportional to. Tell me which one is correct. Okay, see the relation. It's inversely proportional to diameter square, means it is inversely proportional to radius square, right? So the answer is it's inversely proportional to radius square. Okay, okay, this is clear. Good. All right, so then that is the end of questions. Okay, so now see, the questions based on mean free path, they were not asked earlier that much. Okay, so that's why I have limited questions, but then there would be some questions in the worksheet, okay, that you can try, but they will be all, see, they will be all formula based questions, right? The mean free path, it has got this formula, so the question based on it will be formula based question. For an example, let me just give you an example what kind of questions can be asked. Mean free path, lambda mean is given by 1 upon root 2 times n times pi d square. Okay, so this is the formula, I guess. Okay, n times pi d square, right? So now suppose you have one kind of molecule. Okay, so molecule 1 or gas 1 where the having radius equal to r, okay, having size r. Gas 2 has size equal to 2r. Then at same temperature, what would be the ratio of mean free paths? Ratio of mean free paths. So that's very simple, right? Yes, no, it's inversely proportional to diameter square. Okay, it's inversely proportional to diameter square, means lambda 1 is to lambda 2 would be equal to what? d2 by d1 square. Okay, so that is one kind of question. Okay, this kind of question can be asked. So just put that, because it's inversely proportional to d square, diameter square. So whatever is the ratio of diameters, same would be the ratio of radius. Then you can put that. So it will be 2r by r square. So what would be the answer? 4:1. This is one kind of question that can be asked, right? This is clear? Yes, no? Okay, good. Then Next is they can change the density. Okay, whatever can be changed, they can change and ask the question. So suppose again you have the formula lambda mean is equal to 1 divided by root 2, okay, n times of pi d square. Okay, so if for gas 1, or you can say first sample in which you have first gas, where, or if in sample 1, okay, that is in a container, the density of gas is n is the density, right? Then sample 2 will have density n prime is equal to something, right? So for an example, 2 times of n, okay, this is just an example, they can give any value, 4 times of n, let's say. Okay, so what would be the ratio of mean free paths? So again, it is inversely proportional to density. Density means number density. Yeah, density and number density would be same, right? So lambda 1 is to lambda 2 would be equal to what? Okay, if it is same kind of gas, density and number density would be same, right? So lambda 1 is to lambda 2 would be equal to n2 is to n1, right? Lambda 1 is to lambda 2 would be just equal to n2 is to n1. So in this example, in this particular example, it would be equal to 4, right? This thing is clear? Yes, no? Okay, so it is just one formula and the questions that can be asked are limited, but provided you know the formula, you can solve the questions based on mean free path. Okay,